not clearly spoken speech. And to extract information from the speech signal, what kind of features should we extract? There were talks on that also. Then it came to the applications. Some of the secondary applications are how to identify the language in which the speaker is speaking, whether it is Hindi, Odia, or Telugu. And another application is speaker recognition. Who is speaking? Who is speaking? Or somebody says, this is my bank account and I want to access it. Is he the claimed person? The speaker verification. Speaker profiling. Who is the speaker and how is he speaking? What is emotional contents and so on. These are the applications. But the two main applications are automatic speech recognition, which is you give the speech to the machine and the machine recognizes the sequence of words that you have spoken and output is the text, preferably in the native script of the language. So speech recognition or automatic speech recognition is the case where speech is fed into the machine and machine outputs the corresponding text that was spoken. The complementary system is a text-to-speech system where text in the native script is given to the system, output is the speech in one particular voice. So all these have been talked about. So I will be talking today about automatic speech recognition. Now, so automatic speech recognition, ASR is the acronym. Automatic speech recognition of a special kind of speech. That's what I'm going to talk. The type of speech is the speech by people who have a condition, speech disorder called dysarthria. So I will use the term dysarthric speech for that purpose. So here is the outline of my talk. I'll first briefly introduce what is dysarthria. Then I will talk about the elements of the ASR, which ASR is a supervised pattern recognition. It is like learning ABCD children in lower KG. These are right, capital A, capital B, and C, and so on. What is the difference between capital P and capital R? So you have to give examples of capital P, several examples of capital R, so that students will distinguish in them. So it is supervised pattern recognition. So you have to give not only the image in case of ABCD, not only the image, but which letter it is. A label is necessary. In the case of the automatic speech recognition, so we need labeled speech data. So the labeled speech data, and what we plan to do is to have application that helps our people, Indian people. I am in Vijayawada. The native language here is Telugu. So we want to help the people in this region. Therefore, we need speech data that is spoken by people who speak Telugu as the native language. And what should they speak? So we need the text that they have to speak. So we will talk about a speech database development, which has the two parts. One is designing the text that has to be spoken, and the second part is the speech data recording itself. Then we will come to the actual implementation of automatic speaker recognition system, the extraction of the features that are useful for speech recognition, and the models that will do the recognition part. Models are of two types. One is acoustic model, and other is the language model. So in acoustic model, there are various types of statistical and probabilistic models that we will talk about. And briefly, we'll also talk about language model. And then we will talk about at the last 15 minutes, we'll talk about the implementation of a Telugu ASR system that recognizes speech from people who have dysarthria. So there's a performance evaluation. We'll talk about it. So let's go to what is dysarthria. Okay, and why the topic is automatic recognition of dysarthric speech. So all these days, voice-enabled interaction is very common. We speak straight away like this to Google Doc or any other, many other applications, and it gives us answers. So voice-enabled interaction with the computer has become common. It's so convenient for people. So we speak. How do we speak? Why do we speak? We speak because we want to communicate with the other people. That is the goal of speech. So I am speaking. Let's say right now I am the speaker. In my head, I have some thoughts, some concepts that I want to communicate to you. So the brain forms a sentence. Right now I'm using the English sentence, English language. So the language is English. I am the speaker and I am speaking I want to convey something. I want the concept, the sequence of words. I construct a sentence in English language. And then the brain gives instructions to the system that generates speech, vocal system, which could be vocal cords here, the bulge that I see here, that it opens and closes, in my case around 120 hertz time, opens and closes, air comes out of the lungs and it enters the vocal cavity here, and the sound comes out. So the sound is acoustic wave, it requires air communication and the medium, and a person, you are listening this, the sound enters your ear, your auditory system processes the speech and sends nerve signals to the brain, and the listener, that is you, tries to understand the concept that I want to convey to you. So that is the speech communication. Okay. Now, what may happen in this case is when there is the dysarthria. Dysarthria is a particular type of disorder where there can be various types of disorders, ALS, stroke, and so on. When these portions of the brain does not do its job correctly, even if the person with the dysarthria wants to say something, the commands to the vocal tract system do not go that well. So this person is not able to speak. So let's look at a typical scenario of dysarthria. I'm going to do this one quickly because my colleague, Dr. Govind, yesterday morning gave this talk and even showed this video, but I will still go through this video because you will get a reminder of refresh of the idea of what is dysarthria. Dysarthria is a speech disorder, and it can be due to several causes. In our case, in our speech group, is dealing with the dysarthria due to stroke. So let us play this. If somebody please say, I checked that it is able to, you will be able to hear it. Somebody say that when I play it, you are able to hear.
You are from Kerala?
I'm from Kerala. Alpe.
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 Which year you went there? To Boston? To abroad?
Abroad.
When you went? 2010, 15, 20?
Every year. I said was 2000.
13? Oh, good.
I said cross the ship. I go every year in Boston, Miami.
So let me just play this particular part.
Abroad.
Sir asked when did you went to go abroad?
Which year you went there? To Boston? To abroad?
Abroad.
When you
See, the person repeats the word abroad to say that, yes, I heard your question. You are talking about abroad. And still he is speaking, he takes some time.
2010,
1, 2, 3, 4, 5 seconds. He takes time to formulate sentences and to speak it out. And even when he speaks out this way, he is speaking very slowly. So we got some idea of how a dysarthric person speaks. Okay. Now, if the person is speaking, firstly, he is speaking slowly. Secondly, he is also not able to articulate the words as clearly as normal people are able to do. Some of the sounds do not come all right, and so on. So it becomes a sort of difficulty for a listener to listen the speech of a person with dysarthria. So what happens? Firstly, he has difficulty speaking, and secondly, even the listeners have difficulty understanding what he is saying. So as a result, his interaction with the public reduces. So his what's your go somewhere else. I'm in a meeting. So so as a result, he becomes more lonely. So he has two kinds of difficulty. One health difficulty, that he is not able to communicate. Second, his interaction with the society reduces. So psychological difficulty. So the goal that we want to see is, can he use speech technology to help him? Now, what we can do, he speaks, an app picks up his speech and generate the text that is corresponding to the what he is saying. And then it synthesizes whatever the output of this speech recognition system is there, it synthesizes and plays it back. So the listener will hear clear speech and the person will be able to interact better. That is the goal. That's why the topic today is ASR of dysarthric speech. So what is ASR? Automatic speech recognition. I briefly taught, I have some idea in my brain, I speak, I generate wave file, and these wave files are essentially a sequence of sounds, sound symbols, a, I, e, u, kaka, gaga, na. So these are, so the waveform will, different parts of the waveform contains information about different sounds. So it takes small segments of the speech sound and extract features, we call it as a speech vector, so that those speech vectors, this is called short-time speech processing, they are fed to the automatic speech recognition system. So the input to the automatic speech recognition system is speech vectors, and output is the sequence of symbols, which were the word sequence, which the original person has spoken. So that is ASR. We already know about it, therefore I'll not spend much time on this. Now, a typical speech recognition is a pattern recognition. A pattern recognition, it is a recognition of a sequential pattern. What is sequential pattern? Why it is sequential pattern? It is the sequence of speech sound. It's a pattern recognition model. It is a supervised pattern recognition, which means just like the kid in the English medium school learned difference between P and R. P is like this, one standing line, one semicircle, that is P. And in addition to the standing line and semicircle, you also put a line like this, that is R. So you have, the teacher gives several examples to the student learn it. Similarly, even in this particular case, the examples are given. Let's say several examples of the sound A is given, from which from the waveform features are extracted which will distinguish A with E and U and so on. And using that, a model is trained. And so this model, once it is trained, then that trained model can be used to recognize whenever a new input comes. So there are two phases: training, that is learning, and the testing, that is recognition. So these are the two phases. To train, let's talk about the first phase, the training phase. To train a model, you need to give examples, several examples of each label that you want to recognize, pattern that you want to recognize. In our case, they are the speech sounds. So, which means that you not only should give the waveform, but also you should say this waveform corresponds to this sound. In other words, we need a labeled data set. Therefore, now we are dealing with the patients with the speech disorder. Therefore, this is a special kind of speech which is not clearly articulated. Therefore, a speech data from patients with the speech disorder is essential. So now we want to help our people in the Indian language, and that is this ASR from is difficult because the speech of the dysarthric patients are not articulated. Therefore, we want to collect speech from local patients with the speech disorder, and we also want to collect from different patients, lots of patients, more because we need data so that the characteristics of dysarthria with the various degrees of dysarthria from various people, male, female, elders, children, or adults, and so on, all has to be collected. So it is better if it is all. Where do we get these people? We get these people, they come to the clinics, and it is better to collect in the uniform environment and under the supervision of doctor, so that we do not stress them unnecessarily. If you ask them too many, if you ask them to speak too many questions, they may be stressed. Therefore, it's best that that activity is done under the supervision of doctors. So this is where the All India Institute of Medical Sciences, Mangalagiri, comes into picture. This is the location. It says there are hills on all the around side, and this is the campus. Dr. Govinda also showed this. Now we are in Vijayawada. Our campus is on the one side of the Krishna River. About 10 to 15 kilometers is the location called Mangalagiri. So we call this is the All India Institute of Medical Sciences in Mangalagiri, AIIMS Mangalagiri. And AIIMS Mangalagiri is a part of the National Stroke Registry Program, because during the COVID time, stroke incidence increased. Therefore, government started a National Stroke Registry Program, which admits the parents, patients, and collects information about the characteristics that they have, not just speech, but many others. And they also check the stroke magnitude and incidence and so on. So the speech research group at KLEF initiated a collaboration with the AIIMS Mangalagiri to start a data process. So of course, you did a memorandum of understanding, and the speech, since there are people are involved, data collection from people are involved, ethical clearance certificate is necessary, and so we started such work after getting a clearance. And later the AIIMS and our university, Koneru Lakshmi Education Foundation, submitted a joint project proposal to Indian Council of Medical Research. That was granted, and the project for 3 years started 2 years ago. So now we want to record a speech. Why you want to record speech? Because we want to train ASR system so that we can help the people with the dysarthria. What should they speak? Typical text that is spoken is vowels. E. So I call it a sustained vowels. You ask the people to say as well. Yes, pause. Similarly, other vowels. That is one thing that is standard done all over the world, because it's now difficult for people to speak. People with the difficulty in articulating speech. Next, this is just single vowel, single sound. Can we ask them to speak sequence of syllables? That's words. The simplest thing is papa. There are 2 syllables, pa and pa, papa, pipi, pupu. So syllable, bisyllabic words with the pa is easier to articulate also. The articulators here is easier to open and close. And that's the second type of data that we want people to record. Okay. Then our goal is to help the people to speak out normally, speak normal sentences, not just words or vowels, but be able to interact with the people who come to meet them and talk to them. So we want our system to be able to recognize not just vowels or words, but sentences. Now, sentence is a sequence of words. Now, this sentence can be really long. It can be short. I went home, 3 words. Or it can be extremely long sentence. It may have 50 words. People with dysarthria have difficulty in articulating speech. They get tired easily. Therefore, the sentences should not be long. They should be short sentences, and they should be Telugu sentences, because we are collecting data from Telugu people who speak Telugu as their mother tongue. So we need 10 short sentences. What should be the characteristics of these 10 short sentences? So such as sentence we need to record, and to record such data is not available. What should be the characteristics of such sentences? The sentences, if you say short sentences, just 3 words, if everybody says the same 3 words, I'm fine, I'm okay, I need water or something, not all speech sounds will not be recorded. Only certain speech sounds will be recorded. Or will be recorded happily, consonants, many consonants may not be recorded. Whereas a general purpose speech recognition system should be able to recognize any sequence of words. Therefore, it should know the characters of different sounds. All the sounds of the language spoken by people with dysarthria. Which means sentences should be short, yes, but they should also be designed such that different people pick different sentences which contain, as far as possible, all phones of the language. So we say that such sentences should be phonetically rich. So we need to design a set of phonetically rich Telugu sentences so that people will be able to speak them. So the first step in the creation of the phonetically rich Telugu sentences, there are 3 steps. 1, you collect Telugu sentences. You collect Telugu sentences, but pull out only short sentences, because people have difficulty in speaking long sentences. So we decided that we'll select only sentences which is 3 words long. Second step would be to identify phonetically rich sentences. So how do you identify phonetically rich sentences? For every sentence, the sequence of words, each word you convert it into a sequence of phones, different sounds, and then you see which sentence, 3-word short sentence, contain many different sounds. We want to pick those sounds and want people to speak them. So and not just one from some 5 sentences or 10 sentences. We want several such phonetically rich sentences, short sentences. We want to create that. So that is that. So first step is to get Telugu sentences. Where do you get these Telugu sentences? There is a open SLR has lots of Telugu sentences, thousands of them. We download those things. They are freely downloadable. Download them, and we want to identify 3-word long sentences, but which are phonetically rich. How do you know that it is phonetically rich? We need to generate. For every sentence, for every word, we need to generate the corresponding phone sequence. Only then we know that what is the phonetic richness of the sentence. So how do you generate the such a phone sequence? Of course, there is a unified parser, part of the Government of India project, that is available at GitHub. You can use it. So here is an example. So this is a Telugu sentence which has 3 words. I can barely read this sentence, but many of you may not be able to read this sentence. Therefore, I have written the corresponding English version here. So the 3 words, adhikariga, paluchotla, panicheshadu. Okay, so I am reading it. Adhikariga, paluchotla, panicheshadu. Now this unified parser takes up each word. So in this particular case, this adhikarika, it generates it as it writes the corresponding sequence of phones. Adhi has 3 sounds. One is A, and then is Dha, and then E. Adhi is a sequence of 3 sounds. A followed by Dha followed by E. Similarly, Ka is K, A, Riga, R, I, Ga, G, and A. So these symbols are designed for so that they cover most of the sounds spoken by Indian languages. This is part of a previous government project. So this unified parser that we see here, that when it is fed with a sentence of Telugu words, it generates the corresponding phone sequences. Now you see that some phones have occurred repeatedly. For example, vowel A has occurred several times, and what's happening? Yeah. Okay. Yeah, vowel A has occurred here and several times. Okay. So what we need is to select sets of short sentences. Now, if we can select 10 sentences, let's say, also we had some pilot experiments, and we found out that if you ask them to read a lot of sentences, paragraph pages, they won't be able to read. They get tired easily. So we decided that each person will speak vowels, a, e, and so on, words, papa, pipi, pupu, and 10 sentences. Each sentence again containing only 3 words because they get tired. But it is possible that if the sentence, they all read the same sentence, that is no good. But if every person speaks different sets of 10 sentences, that is also not good, because we want to find out the degree of dysarthria of different people. We want to characterize different people also. Well, therefore, what we did was, every person will read 10 sentences, out of which the first 2 sentences are common for each person. Everybody reads the same 2 sentences, which are phonetically very rich. By doing this, text is same, but people are different, so we can also do the speaker characterization. And then the remaining 8 sentences, they are different for different people. So we built 50 such sentence sets. And out of the 8 different sentences, we also felt that it is easier for people to speak digits. 1, 2, 3, 7, 8, 9, 5, 6, 7. Not necessarily in that order. Any combination of digits, it's easier for people to speak. So therefore, the last 2 sentences of the set consist of digit sequences. So this is an example of a sentence set. There are 50 such sentence sets. This is sentence set number 35. The first 2 sentences, this is Koncham Kudi Vellandi. Okay. So these are the common sentences spoken by every people. And the rest of the 8 are different sets spoken by different people. Again, out of the rest, these 8 sentences, last 2 sentences are actually sequence of digits. For example, the sentence number 9 is Tommidi Okati Mudu. That means 9, 1, 3. And so in any combinations of digits, and the last one is Aidu, Edu, Tommidi, 5, 7, 9. Okay, so 50 such sets are designed, and each person speaks different sets. Now that text corpus is ready, and we want to record the speech. When you want to record speech, we have to take the consent of the patient's relatives. And it was recorded in a clinical environment in the hospital ward itself. We also checked that these people take medicines. They take medicines that sort of reduces their activity, physical. It's a kind of sedation. They should not be there. They should be able to. So a couple of hours after they take a medicine, we started the recording. How did the recording? Normally, if you're a healthy speaker, we give them the sheet of paper which contains the sentences, you read them. But majority of the people were over 50 years, and many of them were illiterate. Even if they're literate, they would be so constrained. So so much problem is that they don't want to read a sentence. So we resorted to the following. We had project staff and our research scholars. Research scholars read the sentence. A short 3-word long sentence. Research scholar or project staff read the sentence. Person heard it and he repeated. So, and we started the recording. Start the recording. The scholar reads the first sentence. Person repeats it. Then scholar project staff reads the second sentence. Then the person repeats it, and so on. So everything is recorded in a single audio file. When all the recording is over, recording was stopped, and then then each of the words that are spoken by each person was manually segmented to pull out only the speech of that particular person. Now, sometimes it so happened that some people, their health condition was so strong that they could not even repeat a short sentence of 3 words. So we asked them to repeat 1 word at a time. Therefore, although we devised 50 sentence sets, the last 10 sentence sets that contained just the common sentences and 20 phonetically rich words. So this is for the case of the people who could not repeat even a full sentence in a single shot. So we had to divide this. So they repeated only words at a time. Okay. We started recording speech data in the various phases. In the initial phase of the speech data, we collected speech data from 50 stroke patients, out of which 30 were males patients and 20 were female patients. Now, we also wanted to find out what change in speaker characteristic happens in the case of the dysarthric patients. We also wanted to collect the data from healthy speakers. We also call them healthy control speakers because they speak normally. The healthy speakers also read exactly the same sentence, the same sentence as the stroke patients. So the sentence sets, 50 sentence sets were read by 50 stroke patients, and the same sentence sets were also read by healthy speakers, out of which there were 17 male speakers and 33 female speakers. We try to have equal balance, but what happens is, in case of the patients, most of the patients who come to the hospitals are male people, whereas it's easier to get the nurses and other people from the hospital to healthy people to speak our sentences. So there is some gender imbalance, but we try to do it as much as possible. Okay, so once we collected the data, we have data from 50 stroke patients and 50 healthy speakers. We want to analyze the characteristics of the dysarthric speech. So this talk was given, we studied 2 characteristics. One is F0, that is the fundamental frequency of glottal vibration. The other is durations of the steady and transient segments. This talk was given by Govind yesterday, therefore I'll quickly run through this. So if you look at this, we did this experiment separately for male speakers and female speakers, because male speakers fundamental frequency of vibration, pitch frequency in normal terms, is between around 100 to 200 hertz. And for female speakers, it is from 150 to 300 hertz. So we studied male speakers separately and female speakers separately. Now, amongst male speakers, there are patients and there are healthy speakers. So on the y-axis is the pitch frequency for different overs. We took only over so that there is a kind of thing. The pitch doesn't change depending upon the neighboring sound. Now, in this particular case, if you look at the red bar, that belongs to the healthy speakers. So the blue one belongs to the patients. Now you see that in general, blue ones are slightly higher than the red ones. Therefore, the F0 or the pitch frequency of the male patients is slightly higher. Pitch frequency of patients, that is slightly higher, that you can see here, but male speakers. Now, on the other hand, if you look at the female speakers, the pitch frequency of the patients, the blue one, is slightly lower than that of the healthy speakers. So we see 2 contradictory or different types of observations. One, male dysarthric speakers, their pitch, male speakers' pitch is lower, they try to increase the pitch. Whereas the female speakers, in general, pitch is high. So when they have a difficulty, they tend to decrease the pitch. So that male speakers, lower pitch, they try to increase. Female speaker, their pitch is high, they try to decrease. So they come to the sort of middle. When the articulate, when the muscles are not doing their job well, the frequency vibration sort of comes to the sort of, average value or neutral value. That's first analysis. And second, if you look at a speech waveform here, the waveforms, this is the vowel puram, word puram. This is the word P is here, from here to here is U, from here to here is Ra, and from here to here is A. Sorry, up to here. Now, if you look at the A, it is the F2 is constant here for most of them, and then try to decrease. So there are changes even within the, and then why it decreases? Because at this particular phase, the A is changing to Ma. So this is a transition. Our articulatory system was speaking A up to here, and from here onwards, it should make a transition to the sound M. Now we looked at the durations of the steady state segments and the transition state regions, and we took their ratio. What we observed was that the people with the dysarthria, again, the red bar, those people, their steady state duration was longer and transition duration was shorter. So if they want to say Papa, they say So the any steady state region is longer. Transitions are done quicker because they don't have that much control. So this is one more observation that we made. Govind talked about it. So this is the summary. In case of the pitch, the male speaker tend to increase their F0 from 100 to 150, let's say, whereas the female speakers try to decrease from 250 to 200 or something. And in case of dysarthria, the phone transitions are faster of these patients, and steady states are really longer. So these are the characteristics of the dysarthric speech. Okay, we have done that. Now we want to go back to our application. What is our application? We want to see whether we can use the ASR technology to help those people. We already have seen the video. Now let's go to the ASR. So the ASR, there are three modules. One is extracting features that will be useful to recognize different speech sounds, and using the labeled speech data, train the models. That is the training phase. And when a person speaks some speech, we don't know, the system doesn't know what text it is, but it has the models which are trained to recognize different speech sounds. So that at that point, it uses the trained models to output the text that was spoken by the people. Okay? So there are three blocks, if you see. First block is signal processing block. Second block is training the models, learning. Third block is using or recognition phase. So let's go to each of them. Well, there have been lectures on speech production, so I will not spend your time on this. That the air comes from the lung, that is the source of energy. Vocal folds vibrate, pitch vibration, 150 frequency and so on. And the vibrations propagate through the vocal cavity, that is here, and sound comes out. So this is the speech production. Now the sound is heard by human ear. The outer ear is here, and the ear canal, there is a ear drum here, there is a middle ear here, and frequency analysis or spectral analysis is done by cochlea. The cochlea is a snail-shaped structure, and this cochlea does the frequency analysis. So let us, the cochlea, there are several chambers and one membrane called basilar membrane is the membrane that vibrates when sound enters, and this membrane is about 30 millimeter long. And different parts of this membrane respond to different frequencies. So how does the ear do the frequency analysis? In the inner ear, there's a cochlear snail-shaped structure which has a chamber, which has a membrane called basilar membrane, and this basilar membrane is 30 millimeter long, and different parts of the vascular membrane respond to different frequencies. So let us just look at a video here. I want to just this is interesting to see that. So here is the video. So this is the outer ear. Sound enters the ear canal and goes to the membrane, and then the cochlea is there. For the sake of demonstration, we will stretch it out as a single membrane, basilar membrane. Now we will play different sounds. Let's see what happens. Low frequency, medium frequency, high frequency. All of them are there, different parts also simultaneously. You might have seen this video earlier. So what happened is when only three sounds are there, one individual sounds, only individual portions vibrate and send nerve signals. When that is what is happening here, the low frequency, medium frequency, high frequency, all of them frequency, and also to the brain, and brain looks at this energy at various frequency spectrum, and interprets it. Of course, it also has a MEL frequency, is not Hertz scale, the log linear scale called MEL frequency. Therefore, the popular feature that one extracts even for speech recognition is MEL frequency capture coefficient. You are familiar with this, therefore I'll skip this part. So we have computed MEL frequency capture coefficient. Now let us look at how does the MEL frequency capture coefficients of normal people and dysarthric people, are they different? Yes, because dysarthric people are not able to articulate clearly. So you can see the Tishney plot here in the two-dimensional space, the healthy speakers and dysarthric speakers. There is overlap, but there is also some distinction, which shows that the speech characteristics of dysarthric speakers are different. Therefore, normal speech recognition systems will not work as well for recognizing speech of dysarthric speakers. Therefore, we have to train the system. We do the short time speech processing. Every 10 milliseconds, we take a frame and we compute the spectrum, MFCC capture coefficient. But if you look at the waveform here, it is a sequence of several sounds. Therefore, we want to see how this spectrum varies as a function of time. So we use the spectrogram. You have already seen this. Okay. Now, let us go for the training of the model. So we want to train the models for different speech sounds. So how do we do that? We want to train models. So what is the kind of data that we have recorded? We have recorded vowels, E, and so on. We have recorded words, papa, pipi, pupu. And we have recorded sentences, which are sequence of words. So we need models for these three types of systems. What about vowels? Vowels are characterized by their formant frequencies, resonance frequencies. So in the spectrogram also you can see that different vowels have different frequencies. For example, vowel U has a formant frequency here, whereas vowel A formant frequency here, and so on. The vowel E for second formant frequency is even higher. So the formant frequencies characterize different vowels, and we know this has been studied half a century ago. But different people have different physiological characteristics. Therefore, the vowel E spoken by different people, they do not have the same formant frequency. Children will have higher formant frequency, adult females will have medium-sized formant frequency, and adult male, taller people will have shorter formant frequencies. Therefore, even a single vowel, E, spoken by different people do not have the same format, but they are nearby. So the formant vectors or dot points in the F1, F2 space, they form a cluster. So if you want to have a model for the vowel E, you cannot have just one value. Because it is a cluster. So what you can do, you can find out the center of the cluster, which is given by the mean of the F1, mean of the F2. That gives the x1, x2 coordinates of the center here. Yeah. And then there is also spread. There is a spread along the F1 axis. There's the spread of this cluster along the y-axis. Therefore, you also have to compute the variation along the x-axis and y-axis. That's computed by the standard deviation. So when mean and standard deviations are used to represent one vowel, such a model is called statistical model because mean and standard deviations are statistical features. Okay, we can do that. So statistical models are used, and when a new data point comes, a new data point, let's say, is this cross that you see here, whether this cross belongs to blue vowel or the red vowel. What do you find out? You find out the distance of the cross to the centers of these clusters. Whichever distance is lower, we say that it belongs to red cross. But you also look at the spread. If you consider the only mean, we will say that this class belongs to this data point belongs to vowel, red vowel. Whereas if you consider this standard deviation is very high, therefore you can use a weighted Euclidean distance, and in that case, this data point actually belongs to the blue vowel, and so you can use statistical models to find out a test data to which vowel or sound belongs to. So we talked about statistical model. Now we'll say why a probabilistic model is necessary. Now let us look at the vowels or there's a call vowel, English vowel or call, and this is had, a of had. You see these two clusters are overlapping here. That means are spoken by children, their formant frequencies will be higher, whereas a spoken by tall people, their formant frequency will be lower. So there is overlap between the clusters. When there's an overlap between clusters, statistical models are not that great. Therefore, we use probabilistic models and we use normal distribution or Gaussian distribution that gives the probability of a data point belong to each of the clusters, and we can use higher level knowledge such as the lexicon or language model to improve the recognition accuracy. Second, even if you look at the shape of this cluster, let's look at the shape of this cluster. Whenever you say that this cluster is represented by a probabilistic model, Gaussian distribution, it assumes that the shape of the cluster is an ellipse, perfect ellipse. But let us look at the vowel A, common vowel A. Its shape, yes, after here is fine, but here it is slightly like a bean seed. It is not a nice ellipse. It's not ellipse, it is like this. Therefore, whenever such shapes are not completely ellipse, then a normal one single Gaussian is not good enough. The better to use multiple Gaussians. Such a model is called Gaussian mixture model, and that is used. So how do you train Gaussian mixture model? Okay, let's look at this particular example where, where there are data points. These are there are two clusters. How do you train the cluster? There's an example illustration here. You start with any random mean points, and then it slowly with the iteration it starts forming into the beta clusters. So that we talked about training the models. Now we'll go to the actual recognition using the testing phase, usage phase. Why speech recognition is difficult? There are various sources, variabilities, physiological, emotional, and so on. And this is normal people, and this is even more difficult for people with the dyslexia. They are speaking sentences. Sentence is a sequence of words, and and word is a sequence of phonemes. Therefore, what we are interested in here is recognition of sequential patterns. Dynamic time warping is one old method. We can use a statistical model, probabilistic model called hidden Markov model. We can use a combination of these HMM, GMM. It's a sequence. And how do you model a sequence of symbols? Well, speech is a signal. What do you mean by signal? It varies with the time. Signals are of two types. One is called deterministic signal. Let us look at the traffic signal. Initially it is red, then amber, green, amber, and comes back. We can predict the sequence of the different symbols coming one after another. In fact, even the time it can be predicted. On the other hand, look at the weather pattern. That it is sunny, it is cloudy, it is raining, and it is cloudy. Which comes after which? There is no way of specifically saying which weather state comes after which weather state. Therefore, it is called a stochastic signal. And for stochastic signals, we use a probabilistic model. Then scientist called Markov proposed such a model. Therefore, this model is called Markov model. And what we see is that even this Markov model alone is not sufficient. Let's look at why that is so. Here is a spectrogram of the word Thiruvananthapuram. Thiruvananthapuram. A North Indian spoke this, so he spoke it as Thiruvananthapuram. Mispronounced. That's okay. Normal, healthy person. Now, so here is the waveform, and here is the corresponding spectrogram. And the red bars that you see here are the formats. This is the second format, what I highlighted. And the format, the oval U has occurred here in Thiru, and it also occurred here in Puram. So the oval U has occurred twice. Now let us concentrate on the second format of the oval U. So the oval U here is the format, second format is decreasing. So I'll just highlight that. U, second format is decreasing. Whereas the same oval U spoken with the same person, in the word Puram, the second format frequency is increasing. Here it is increasing, whereas here it is decreasing. So the same vowel in different sound contexts can either increase or decrease. So let us look at the same word Thiruvananthapuram. We concentrate on the vowel A. The vowel A has begun somewhere here, here around 700 millisecond and at around 820 milliseconds. So let us look at the second format frequency of the vowel A. It is constant. At the end, it decreases. Why? Because the second format frequency, next sound ma, is smaller. Therefore, even within one vowel, it is constant decreasing. Now let's look at the F3. F3 is here. F3 is slowly increasing and then constant. Slowly increasing, constant. Let us look at the F4. F4 is decreasing initially and increasing. Let's look at the F5. It is initially increasing and then decreasing. So you see that different formats also vary differently. One can increase, one can decrease for the same speech sound at the same context. Therefore, if you look at the variation of the format frequencies of one vowel A, first format frequency was nearly increasing, steady. Second format frequency of constant and then fell down. And the third format frequency increased and steady. Fourth format frequency was decreasing and then increasing. Fifth format frequency was ulta. So even within one sound, format frequency change. Therefore, we should not treat even one sound as a single unit, but as a sequence of 3 units. The middle part, which is reasonably steady, doesn't change much of time. Left part, that depends upon which sound was spoken earlier, and the right part, which depends upon the next speech sound. So we represent each sound as a sequence of three parts. In hidden Markov model, they are called states. The word is state. So each sound is recognized, is modeled as a sequence of three states. The three states are written down here. Each state, again, within the each state, formats are varying. Therefore, associated with each state, there is a probability distribution. So there are three states, therefore there are three probability distribution, and the duration of the middle segment is longer, therefore there are certain transient probabilities and so on. So hidden Markov model represents each speech sound as a sequence of states. And of course, we said that for each state, there is an associated distribution, and this distribution need not be a normal distribution, symmetric curve, and so on. Therefore, we can represent it by a Gaussian mixture model, as we talked about it. So together, a hidden Markov model normally uses the Gaussian mixture model and a hidden Markov model. This is the popular one that is used. Of course, we have in the last 2-3 decades, neural networks have become popular, and they are inspired by how human brain works. So the neural networks take inputs. The inputs in this particular case would be the, let's say, MFCC feature vectors, MFCC coefficients, 13 coefficients are there, or it could be format frequencies. The evidence from the various format frequencies are combined together to figure out which vowel was spoken. That's an example. We can extend it. We can have layers of neurons. When in some 3 decades ago, when the number of layers of neurons were 2 or 4, that such a system was called deep neural network. These days, deep neural networks have tens of 50s of layers. But so the feed forward neural network, I'm skipping it. So what is the difference between Gaussian mixture model and deep neural network? Normal deep neural networks are discriminative model. What is a discriminative model? Deep neural network is trained to distinguish between similar sounding vowels or consonants. Let's say pa versus pa. Little bit of aspiration, meaning changes. Pal versus pal in Hindi, for example. Therefore, GNN is very good in distinguishing these two things, whereas a Gaussian mixture model is a generative model. It characterizes characters very well, but it's not that good in discrimination. Therefore, instead of using GMM, HMM, with the people use DNN, HMM. So we will be talking about DNN, HMM as our model, where DNN, HMM, Gaussian mixture model is replaced by the DNN. Now, we'll go to the recognition of a word. Why do we want a word HMM model? Let us look at this particular Telugu sentence. I'll just read this. This is written, and the corresponding, it is also written in English here. It is Migata Bhagam Panidi. There are 3 words. Vigata Bhagam Panidi. That is the correct pronunciation. And we asked one person Disatria, whose speaker ID is 237, to speak the sentence. It is the sentence number 4 and store it in the wave file. This is Telugu, therefore TL. See, the file names are informative. Its first 2 its letters and digits alternate each other. This is Telugu language. Speaker number is 237. He is a male speaker, and his dysarthria level, degree of difficulty is 1, and he's reading the sentence set number 336. His degree of NAS score is 6, and his sentence number 4. File names are informative. So let us look at this wave and let us play this. We are the person to speak a sequence of 3 words. Let's play it. Let's see how he speaks.
Magata Baram Tardi.
Let me play it again.
Magata Baram Tardi.
Let us concentrate on the first word. He supports say Migata. He says Magata.
Magata Baram Tardi. Magata
Magata.
Baram Tardi.
So the first word is also not pronounced correctly. Now let's look at the second word. Bhagam.
Magata Baram Tardi.
Bharam. Bhavam. He doesn't say Bhagam. The third one. Panidi. Let's look at how he speaks the third one. Panidi.
Magata Baram Tardi. Magata Baram Tardi.
Tardi, he says. He's not saying Panidi. So reading even a short sentence of 3 words has become difficult for him. So what we did was, when he had difficulty, we asked him to read only first 2 sentences once, and then not repeat first 2 sentences and then the last sentence. And what happened as a result is that his pronunciation improved. Let me play this. Earlier, Migata, he spoke it as Magata. Now let us see.
Megita Baram. Megita Baram.
Migata at least came all right. But Bhagam, slightly better, but not that great.
Megita Baram.
Bhagam has not changed. Now let's look at the Panidi. Earlier he said some Vanidi or some such thing. Now
Pardi. Pardi.
A has come out already. So why am I playing this? To show that for certain people, the degree of dysarthria is so strong that they cannot even speak a single sentence of 3 words. So we wanted to do that. So we wanted to prompt them only 1 word at a time. Therefore, we first experiment, ASR experiment that we do deals with the word. Recognition of a word, 1 word spoken by dysarthric people. What kind of models did we use? We use 3 types of hidden Markov model. One is called the monophone, other is called triphone. These are 3 versions of the context dependent models. We could not use DNN because amount of speech data was small. Now we wanted to check how the performance of a speech recognition system that recognizes a single word from people with dysarthria works. So we want to know how it works with people with dysarthria. Therefore, our test data is only speech from dysarthric people. We will not use this data for training the system, so that we know the performance system for unknown speakers. So there are 2 dysarthric speakers, and one of them is male and female. So we took the gender balance. And now we tested, we found the performance of the same set of test data with the 3 types of models. Models that are trained only with healthy speakers, and in the next page, models that are trained with not only with the dysarthric speakers, and models that are trained not only with the healthy speakers but also with the dysarthric speakers. Let's look at their performance of the system. Performance of the system is measured by word error rate. It's error. Therefore, lower the better. So higher the accuracy, lower the word error rate. Now, if you use a monophone model, that is the simplest type of model, context independent model, the word accuracy is around 68%. We went for sophisticated model. We expected lower word error rate, but sophisticated model did not give that performance because the amount of training data was very small. These are the words spoken by people. Therefore, the amount of data was small, and the triphone models are big models, billions of data parameters to train. Therefore, they did not do well. Now, this is the situation when the model was trained with the only healthy speakers, 14 male and 30 female. Now, let us see. So healthy speakers, the system knows how to recognize clean speech or clear speech, but it is asked to recognize dysarthric speech, so it is doing poor. The recognition error is higher. Now, let us train the system with the dysarthric speakers only and ask it to recognize. Let me go back. So what we'll do is now we'll talk of matched condition. That is, system was trained with the disastrous people's speech and system was tested also with the disastrous speech. So it's called a matched condition. And then the errors slightly are lower. So in the earlier case, error was more than 60%. Now it is around 60%, for example, mono. Now, what if we use both the data? That is, data from healthy speakers and also dyslexic people to train the system. Now we have more amount of data. When the amount of data is more, the performance improved much. Word error rate decreased. The lowest word error rate was below 40% for monophone, and even you see that complicated models also performance started changing. So this is the situation where a person is able to speak only one word, and here is a summary. What does the summary says? Summary says that the experiment number 1, that's the blue one, this is the word error rate when the system was trained with the clean speech, healthy speaker speech, tested with the disastrous speakers. Error is high. The red one, the system was trained with the disastrous speech and tested with disastrous speech. Matched condition. Error is slightly lower. But when the system was trained with both disastrous speakers and healthy speakers, it had more data to learn the characteristics of the disastrous speech. Therefore, the system did better and the word error rate was 38%. So we talked about word recognition. Now we go to the sentence recognition. In a sentence, let's say look at this particular sentence, there are 3 words here. So it may so happen that the word, this actually person spoke, John was happy, but the system recognized as John was hoppy. Can you see the word hoppy? Hopping. So it's an error. So this is called a substitution error. Similar sounding word, instead of it recognizing happy, it recognizes hoppy. So it's a substitution error. Sometimes it may say that John happy. John was happy, was word was deleted. It couldn't recognize it. Then we call it as a deletion error. Then it can even be insert some words. John sure was happy. There's an extra word. So this is called an insertion error. So a speech recognition system recognizing sequence of words can make 3 types of errors. All the errors have to be added when you compute the word error rate. So in principle, it can go even 100%, more than 100%. So the word error rate is computed as follows. In the it's a ratio. In the numerator is the sum of the substitution error, deletion error, and insertion error. And the denominator is the total number of words that is actually spoken in the reference case. Okay. Now, this is the word error rate. So for recognition of sentences, sentences also have grammars. Sometimes grammar, so in natural language, there is also a language model that is involved. There are not just acoustic source of information, there are other source of information. That is, what sequence of sounds are legitimate words in the language? What is the grammar? What about the semantics? Meaning sometimes makes helps the system. So let's just give an example. So if the system, the person said, system recognizes wreck, a nice beach. Wreck means spoil. But actually, the correct one was recognize the speech. So this acoustic model was not that great. Therefore, the output was wreck, a nice beach. But if you use a language model, which said this sequence of these words is low probability, whereas sequence of these 2 words is high probability, then using the linguistic information, the performance of the system improved. Therefore, language model is also used. Okay. Now, this is the last experiment that we will be talking about. We want to recognize sentences using not only the HMM model, statistical model, but also using a deep neural network. For that, we need more data. Therefore, we use a larger number of data, 100 healthy speakers and 100 dyslexic speakers in the space 2. And we wanted to test the performance of a system when the speech recognition system is fed by dysarthric speech, unclear speech. But we built several models. One model was trained with one type of data, another model was trained with another type of data, and so on. So we wanted to see for the same test speech, what kind of training data would give better performance. So we trained 3 models. Since we want to compare the performance, we kept the test speech as the same for all these 3 experiments. Test speech was speech from disaster speakers. How many disaster speakers? 8 disaster speakers, out of which 5 were male and 3 were female, 72 sentences. So the same set of 72 sentences are given to different models trained with different training data, and we compare the performance. Now let's look at the model. So the expanded data set, it used 100 disaster speakers data, 100 healthy speakers data, and the performance was checked with all 5 types of models: mono, try 1, try 2, try 3, and also it includes HMM DNA. When the system was trained only with the disaster speakers data, the monophone model word error rate of 48, and as we go towards sophisticated models, the error rate decreased. That's a good news. If you use sophisticated models such as context-dependent triphone models or DNN, with enough amount of data, the word error decreases. That's good news. But this is the model where the system was trained with only disaster speakers data. Now let us train them more, but disaster speakers data, there were not that many wave files, so the number of wave files is small. Now let us train the system with the control speaker data. There are many people, number of wave files was larger. And since the number of wave files, training wave files is larger, the recognition word error rate decreased. Monophone word error rate with the 770 speech files for 48.5%. When it was trained with the larger number of data, the 1000 files, it reduced to 33.9%. So you see that with increasing amount of data, the error rate decreases. Of course, if you use not just disaster can control, but both disaster can control, total number of training wave files increases and the word error rate reduces even lower, 24.2%. That's the first point. Second, if you look at the various models, if you go to the better models, the word error rate decreases to as low as 10%. So it established 2 things. One, you need more data to have a good performance speech recognition system, but collecting speech data from disaster speakers is a difficult job. And second, it's good to go to sophisticated models if you have more data. So the lowest word rate was 10%. When the model was trained with all the speakers data and DNN was used. What was the test data? Test data was 72 sentences from 8 disaster people. Somebody may ask, maybe you cheated us. You chose those 8 disaster people whose performance is good. How do I know that it was for another set of 8 people? So this is a problem that is faced in pattern recognition. Therefore, we do not report the results on one test data, lowest error on one test data. We do what is known as cross validation. So in this particular case, we did a 5-fold cross validation where speech data set was put up into 5, divided into nearly equal 5 parts, 5-fold. One part was taken as testing, other remaining 4 parts were used for training the system. And then next time, second 1/5 part was used for testing, and remaining ones were used for training, and so on. So by doing this, the dependence on test data reduces. So what we report is the average of the average of the word error rates of the 5-fold cross validation. And as you see here, the average now is 18%. Earlier it was 10.6%, 18%. This is more representative. Secondly, we also did the other experiment that this five-fold validation, when when this data was trained with the only control speaker data, error was higher. When it was also trained not only with the control speaker data, but also the speaker data, error was lower. So it again points out the need for larger amount of data. Okay, how large can you go? Well, the data collection phase is over. Now we have data from 300 healthy speakers and 300 disaster speakers. We did the five-fold cross-validation experiment and we reported the errors. And we also try to do data augmentation by changing the speed with which the speech is spoken. We have either made it faster or slower. So this is called a tempo augmentation. And tempo value was 1.0 means no change, but tempo 0.95 means faster speaker. 1.10 means make it slower and so on. So we did the experiment with the various kinds of tempo data augmentation. Data augmentation tempo did not make much difference. But here, this is the last slide that I am showing that when we use a large set of data and when we use a sophisticated model which includes the DNN, deep neural networks are discriminative model, what is the error? Error is around 14%. So error is 14% when you use a large data set. On the other hand, error is about 30% when we use only 100% to speakers database. This points out the two things. One is use large data set. If large data set is not there, you try to do the augmentation. We are still working on it. And use discriminative models, use DNN. So this is the experiment that we have done. So let me come to the summary slide. Our goal was to help people with dysarthria. They have difficulty in articulating. Specifically, we concentrated on people with dysarthria due to stroke. So the goal was to employ the speech recognition system, speech technology, recognize the unclear speech, and then synthesize the clear speech so that listener will have less effort in understanding what the dysarthric person is saying. So the goal is to increase, he would have reduced social interaction, we want to improve it. So, speech technology. One of the work that was done was to do a speech corpus from Telugu people who were speaking dysarthria, so that Telugu people, so that it can be built, an app can be made and it will be useful to the people. And then we did the ASR system with the various amounts of speech data. So there is a difficulty in this connection with the dysarthric people. We try to help them. And what we also saw example of a person with example of a dysarthric speech. We used a hidden Markov model, probabilistic model, which represents a sequence of sounds. And we also found that the lowest word error rate of around 14% was obtained when we used speech data from 300 healthy speakers and about 300 dysarthric speakers. And also we used DNN, that's the discriminative neural network, right? Sorry, deep neural network with this 3-4 phase. Of course, you can know we are in the process of using the current days deep neural network means temporal models, recurrent neural network, encoder decoder model. So these are all the things that we plan to pursue in the near future. So that is a summary of our work that we have done with the recognition of dysarthric speech in the Indian context. Of course, there are other labs which also have done similar work, but this probably we are concentrating only on the stroke affected people. This is where I stop. Thank you for listening. If anyone has any queries or comments, I'll be happy to respond.
Sir, you are muted. Unmute yourself.
Oh, thank you. Yeah. Yeah. Thanks, friends. It was nice. Well, I thought it would be interaction, but still now we are nearly at the end of the session. I'll share the slides with Dr. Dash, and if anybody wants to look at it, do the. And there is the email at the end of the. Too many class, huh? Okay. Thank you. Okay, and Dr. Dash, shall we end the session? It's over to you. Okay, it's lunchtime. Let's break for lunch. Thank you.
Thank you, sir. Thank you.
Samudra sir? I think somehow sir has left or not. Sir, are you there? So, Tadali ma'am, I think somehow sir has quitted. I don't have his number. I mean, mail ID is there though. So, what we will do? We will wait or already 1:30? We will left the meeting. Anyone can unmute? Sona? Hello? Am I audible?
গোটা 30 দিন ছিল না ওটা একটু